In this section, we take a look at the dot product of vectors, as well as the projections of vectors.
Now, why is it called the dot product? Because we use a dot to represent it. So let's see here. Definition. Let U be given by the form U1, comma U2. Okay? Now let's take another vector V, and let's have that be given in component form as V1, comma V2. So let's start off with those two vectors. Then the dot product, and that's what we're defining. We're defining dot product. U dot V. Notice it's called the dot product because of the symbol we use. We use a little dot. You say, well, wait a minute. If you're specifying dot product because you're using a dot, will there be another kind of product that doesn't use a dot? Yeah, that'll happen in later courses. In this course, the only ones we care about are the scalar product, which is when you multiply a vector times a number, and the dot product when you multiply a vector times another vector. Scalar products didn't have anything in between. It was just a number followed by the vector, like 2v or 3u. The dot product actually has a dot in between. There, in later courses, is going to be something called the cross product, which we'll use like a little cross instead of a little dot. But we don't worry about that here. In this class, the only ones we care about are the scalar product, which we've already seen, and the dot product. So here, the dot product is given by, you're going to take the sum of the component-wise products. You're going to do what? You're going to take this first one times this first one, U1 times V1. Separately, you're going to take U2 times V2, U2 times V2, and then you're going to add those together. This is the sum of the component-wise product. You take the components that are the same, the first component, multiply those together. Second component, multiply those together, and then you add them. It's the sum of the component-wise products. All right. So as an example, let's say we have the vector. So let's just find the dot product of 3, 5 with 2, -4. Okay. When you take the dot product of two vectors, you're going to get a scalar. Here, notice, multiplying these two numbers gives you a number. Adding another number gives you a number. So notice this right here, if you take the dot product of two vectors, you're not going to get another vector. You're going to get a number. You're going to get a scalar. Okay. If you multiply a scalar times a vector, you're going to get a vector. If you multiply a vector times a vector, you're going to get a scalar. Right. Here, the way this works is you take these two numbers and multiply them together. So it's going to be 3 times 2. Now you're going to take these two numbers and multiply them together. The second component times the second component. And then you're going to add. Okay, well that's going to give us, let's see, that's 6 plus -20. And that is going to give us -14. So the dot product of those two vectors is given by the number -14. Okay. There's going to be a few properties of the dot product, meaning as long as you're taking the dot product, there's a few things you can kind of take for granted. And the properties of the dot product are reminiscent to a lot of properties that we have of just normal multiplication. Okay, assuming that you're going to take your three vectors, let U, V, and W be vectors. Let, I guess we'll continue using C like we did before. Let C be a scalar. Then all of the following things are true. First of all, commutativity is still a thing, meaning I can multiply in whatever order I want. So if I multiply U with V, that's the same as multiplying V times U. Remember, that's not always true. In algebra, we learned that matrices do not have commutative multiplication. For two matrices, A times B is not the same as B times A. But for vectors, it is. U dot V is the same as V dot U. I mentioned earlier something about a different kind of product. We're not going to worry about it in this class. But there is another kind of vector multiplication called the cross product. That one will not have this property. Cross products are not commutative, but dot products are. You can change the order however you like. The second property of the dot product is distribution over multiplication, meaning you can still distribute the way you have with just regular numbers since forever. Here, u times v plus w is going to be u times v. Oh, I should put a dot in there. U dot v plus u dot w. So here you can distribute there and there. Distribution still works. So this is commutativity. Distribution still works. Let's see, what else? Distribution can work from either side. You can distribute from the left or from the right. So if I have this or this, if I have a vector being multiplied times a sum on the left, right here, here's on the left side, or here it's on the right side, it doesn't actually matter. I can still distribute this either way. So this would still be, let's see, v times u, v dot u, and this would be w times u. Okay, so it'll be plus w times u. Like that. So you can distribute in any direction. You can say, okay, this one's by itself, I'll distribute in, or here these are together and this one's by itself, okay, I'll distribute out like that. In other words, distribution works in either direction. Doesn't matter if the thing you're distributing is on the left or if it's on the right. Okay? Associativity is still a thing. Meaning you can group things however you like. So you can take scalar dot a vector, not dot a vector, a scalar times a vector dot another vector, like this. And that's the same as if you said, well, you know what, let me go ahead and scale that vector first. And then let me multiply that times the vector v. And that's associativity. You can group however you like. And 5, let's say you're going to take the vector u and you're going to find its dot product with the 0 vector. And you say the 0 vector. What's a 0 vector? A 0 vector is a vector that has both of its components equal to 0. So here, let's go ahead and write that over here. Let C be a scalar. Let the 0 vector be given as a vector where all the components are 0. That's what we mean by the 0 vector. If you take a vector, dot it with 0, that's the same as if you took the 0 vector and dotted it with u, and that's just going to give you the 0. Right? So in other words, anything times 0 is still 0. Now be careful. This is the 0 vector. It looks like that. This is the 0 scalar, or in other words, the number 0 that you're used to. These are not the same. This is a vector in space. This is a number on a number line. So be careful with that. Number 6, if you take the number 0 and you use it to, actually no, that should, well, I'll write that out, although this one doesn't belong here. This has nothing to do with the dot product. But it's true, so let me go ahead and state it anyway. If you take a vector u and you dot and you just scale it by 0, you're going to get the 0 vector. So here, that's actually my mistake. This has nothing to do with the dot product. These are all supposed to be products, properties of the dot product. So here, this is true. 0 times any vector is the 0 vector, but that's not the one I was supposed to say right now, because that has nothing to do with the dot product. The last property we're going to have for the dot product is going to be u dot u. If you take a vector and dot it with itself, you're going to get, and this one's a little unexpected, you're going to get the magnitude of the vector squared. That one's a little unexpected. So here, these properties are really a theorem. So we could prove all of these. Now, I'm going to only prove the first one and the last one. You say, what about all the ones in the middle? 2, 3, 4, and 5 are all proven just like you proved number 1. So here I'm going to prove number, I'm going to go ahead and prove number 2 and number 5. All the other ones are going to be the same as those. When I say the proofs are all the same, what I mean is they're done the same way. You say, well, how do you prove something like that? Easy. We know what those are because we can write them in component form. So here I'm going to prove number 2. I'm going to say U dot V plus W. Okay, well, I can write that as U dot, and now V, let me write it as V1 comma V2 plus, and let me write W as W1 comma W2. And you say, why didn't you worry about that one? Oh, because these are in parentheses. They go first. Okay, so let me just add these together. Okay, so that's going to be U dot V1 plus W1, comma V2 plus W2. After all, that's how you add vectors. You add vectors by saying first component plus first component gives me my first component, second plus second gives me second. Okay. Oh, but now the vector U can be written as U1 comma U2, and now that's going to be dotted times this. Here I've already added them, so now let me move on to the dot product. That's going to be V1 plus W1, comma V2 plus W2. So notice my proof just involves writing things out the long way. Okay, but now I know how to take a dot product. The dot product tells me to take this first component times that first component. So it's going to be U1 times V1 plus W1, V1 plus W1. And then let me take U2 times that one. That's U2 times V2 plus W2. And then those are added together. But notice that this is just a set of numbers. These aren't vectors anymore. All I've done is I've said, okay, this number times the sum of those numbers, and this number times the sum of those numbers. These are vectors, but the things inside are just regular numbers. So here, because they're regular numbers, I can do the same thing I always do with regular numbers. Let me distribute. So I can write this as U1V1 plus U1W1 plus, and then same thing right here, I can write this as U2V2 plus U2W2. Oh, but notice now, this is U1, U1, U2, U2. Well, you know, let me reorder these. After all, these are just additions. A number plus a number plus a number plus a number. I can add numbers whatever order I like. So here, let me write this as U1V1 plus U2V2. All I'm doing is I'm writing this one first, and then I'm moving this one right here. I'm just reordering them. I'm going to go ahead and put this one third. So I'm going to write that one as plus U1W1. And then let me write U2W2 at the very end. So that one I'm just bringing straight down. Yeah, but notice what that is. U1V1 times U2V2. U1V1 plus U2V2. That's just the dot product of U and V. So here, these two right here are just the dot product of U and V. Oh, what about these right here? Well, these look the same. U1V1 plus U2V2. Oh, but these aren't V's, these are W's. Okay, so instead of having the dot product of U and V, now I have the dot product of U and W. So that one right there is the dot product of U with W. But there's a plus sign in the middle, so I'm adding those. Oh yeah, that's what I was trying to prove. If I start off with U dot V plus W, that's the same as U dot V plus U dot W. And I should write these as vectors. And there we go. That's our proof. If we start off with U dotted with the sum of V and W, at the very end, we get U dot V plus U dot W. And that's our proof. Okay. 1, 3, 4, and 6 are proved exactly the same way. You basically just take this side, write it out the long way, write it out using the component form, rearrange terms, and at the end it should give you this one. Same thing here. If you write this in the long way, in the end it'll give you this one. Same thing here, and same thing here. So here, the proofs of 1, 3, 4, and 5 are pretty much the same. proofs of 1, 3, 4, and 5 are similar. Incidentally, if this is the last math class you ever need to take, well, then just take this for granted. Okay, well, whatever. If you're going to take math classes after this, my suggestion is you go ahead and actually try these. Try to prove 1, 3, 4, and 5. Because manipulation of vectors is something that becomes very useful, in fact, very central to some things later on down. In particular, calculus, we eventually get to the calculus of vectors. And being able to do these manipulations is something useful to you. And so here, I'm going to go ahead and prove number 6. It's got a similar proof to this one as well. You're going to write it up the long way. It just looks a little different. So here, let me take u dot u. Okay, well, if I write that out the long way, that's u1, comma u2 dot u1, comma u2. And given the way I've defined the dot product, that's just going to be multiply the first set of numbers, u1 times u1, plus u2 plus u2. Not plus, times u2. Okay. Oh yeah, but now that's a number times itself. I can write that as a square. So that's going to be u1 squared plus, and same thing here. That's going to be u2 squared. Okay. Now I'm going to write this in a weird way. I'm going to write this as the square root of u1 squared plus u2 squared squared. All right. Here, a square and a square root would cancel out. And you say, no, they only cancel out sort of. You have to worry about the positive and the negative, right? Don't you have to worry about absolute values, things like that? No, because these are both positive numbers. Here's a square of a number, which is positive. Here's another square of a number, which is also positive. And if I add two positive numbers, well, then that's got to be positive. So if I have a positive number, then I don't have to worry about positives or negatives. It's all positive. So here the square root and the square root will cancel out. And here, that this bottom line is the same as u1 squared plus u2 squared. But if I don't let them cancel out, notice this is the definition that we gave at the beginning of this section. Namely, if I take the square root of the sum of the squares of the components of a vector, that's the magnitude of the vector. Square root of the sum of the squares of the components, the square root of the sum of the squares of the components is just the magnitude of that vector. So here that's going to be the magnitude of the vector. Oh, but there's a square out here. Okay, so it's the magnitude squared. And that proves our last property. Okay, so as our last thing in this section, you might say, all right, so you've defined addition, subtraction, and that makes sense just geometrically. I'm adding two vectors. That means I'm taking the effects of one and adding it to the effects of another one. Here's the effect of one vector. Here's another vector. And if I add their two effects, well, that's going to give me one big vector. Okay, cool. And subtraction and scalar multiplication, all of those make sense geometrically. What's the dot product? How does that make sense? I mean, okay, you're telling me that's what that means. The product of two vectors is done this way. Why? You know, what purpose does that serve? Why is that the definition of a dot product? Why don't I define it a different way? Well, just like most things in math, it's defined that way because that's what's useful. What do you mean that's what's useful? Well, let's take a look. It doesn't, when we look at a dot product, we're not saying you can't define it geometrically. It's just harder to define it geometrically. But we can still do that. And in fact, let's take a look. So you'll remember that when we define vectors geometrically, we say, okay, here is a vector and here is another vector. And let's just give these vectors the typical names of u and v. Okay, and one of the things that we saw was that if you have the sum of the two vectors, that's going to be right here, right between the two. It's going to be longer than either of those. But we also saw that the difference of the two vectors is going to be connecting from here to here. We saw that in the previous section. And in fact, if you take from the end of v down to u, we simply saw that was defined as u minus v. Okay, so if this is the vector u and that's the vector v, u minus v is this vector. And that's something we saw in a previous section. Okay, so what? Well, let's see here. I'm trying to do things analytically. I'm trying to do things on a coordinate system. So let's say that's my coordinate system. All right, well, at the end of this vector v, I have some coordinates. I can say or I can say v1 and v2. Notice that's not the component form, that's literally just the point right here. Oh, but that means I can write it in component form this way, because after all, these do start at 0, 0. Likewise, this is the point u1, u2, and since it starts at the origin, I can write this vector as u1, u2, like this. All right, so there's my illustration. I have this vector, which I can give in component form. Here I have another vector, which I can give in component form. And then here's the difference between those two vectors. Okay, cool. So now what? Well, now let's talk about angles, because that's the one thing that's been missing in all of this talk about analytic vectors. And that is, okay, I can talk about the direction angle of a vector, but notice I keep having all of these shapes. Here's a triangle. What's the angle here? In other words, what I want to do is I want to find the angle between two vectors. Okay, how do I do that? Well, notice this is just a triangle. Okay, so let me draw a triangle. In fact, let me just draw it over here to the side. I'm going to draw the exact same triangle, but without it as a vector. It's just a regular triangle. So here, what I'm going to do is I'm going to say, well, if that's the vector u, then the side length of this is the magnitude of u. Okay, and if that's the vector v, well, then the length of this is the magnitude of the vector v. And finally, if this is u minus v, right here, u minus v, then the length of this will be the magnitude of u minus v. Okay, so what? Well, I know what each of those are. I know that the magnitude of u is given by the square root of u1 squared plus u2 squared. Right, that's how we find the magnitude of vectors. Take the square root of the sum of the squares of its components. Likewise, the vector v, we're going to find its magnitude the same way. That's the square root of v1 squared plus v2 squared. Just like that. And then we're going to find the magnitude of this. Okay, so we're going to find the magnitude of u minus v. Well, notice, how do you find the vector u minus v? Oh, well, let's see. If I have u minus v, I'm going to take the vector component, the first vector component of u, and subtract away the first vector component of v. So that one's u1 minus v1. And then to take my second component of this difference, of this red vector, I'm going to take, well, that's u minus v, and we take the second component of u minus the second component of v. Just like that. So if I want to find the magnitude of that vector, I'm going to take each of those, I'm going to square them, u1 minus v1, I'm going to square that, plus I'm going to take u2 plus v2, oh, sorry, that should be minus v2, and I'm going to square that, and I'm taking the square root of both sides. Okay, so now what? Well, notice this is a triangle, and I'm trying to figure out this angle right here. And I can use the law of cosines for that. The law of cosines tells me that if I want to find this angle here, I can start off by saying, well, look, let's say that this was like the angle C. Well, that would make this the side length little a, that would make this one little b, and that would make this one little c. So the law of cosines tells me I can take c squared is equal to a squared plus b squared minus 2ab times the cosine of the angle C. Yeah, but I know what all those are. If I take my little c squared, that's just this thing squared. Oh, that's just this thing squared. So that's going to be the square root of u1 minus v1 squared plus u2 minus v2 squared. All right? I'm taking, that's my c. That's that one right there. Oh, but that's equal to that square root. So this must be c. This must be my little c right here. Okay, so I'm going to take that guy and square it. And that's going to equal to, well, notice, the magnitude of v, that's my a. So that's going to be this one. And the magnitude of u, that's my b. So that's going to be this one. Just like that. Okay, so that's going to be a squared. Okay, so take your a and square it. Okay, there's my a. And I'm going to square it. And then I'm going to add, I'm going to take my b and square it. Oh, that should be a u1, u2 squared. And square it. Minus 2 times that one. So square root of u1 squared plus u2 squared times v1 squared times v2 squared, plus v2 squared. Finally, times the cosine of the angle C. Well, here the angle C is theta. So that's going to be times cosine of the angle theta. Okay. So all we've done is we've used the law of cosines. C squared is equal to a squared plus b squared minus 2ab cosine of C. Notice that the squares get rid of all of those square roots. So here we can write this down quite a lot simpler by writing it without the square roots. This is now u1 minus v1 squared plus u2 minus v2 squared is equal to v1 squared plus v2 squared plus u1 squared plus u2 squared. All of those are getting squared, so the square roots go away. Here, nothing got squared, so that's going to stay as it is. It's going to stay minus 2 square root of u1 squared plus u2 squared, square root of v1 squared plus v2 squared, cosine of the angle theta. Okay, so now I can actually square this out. This is a binomial. I can square it out. So if I square this one, it's going to give me u1 squared minus 2u1 v1 minus v1 squared. Remember, when you square a binomial, you don't just square each number. You got to take u minus v times another u minus v, and that'll give us this one. Plus, now I'm going to do it to this one as well. All right, so this one's the first one. And now the second one. If I square this one out, it's going to give me u2 squared minus 2u1v1. Oh, sorry, u2v2. I'm dealing with v1, u2v2 here. Minus v2 squared. And again, if I square this one, I get this one. And if you have any question right now saying, how did you square that? Stop the video and do that yourself. u2 minus v2 squared means u2 minus v2 times u2 minus v2. And you're going to distribute. That should give you that. Over here, I'm not going to do anything. I'm just going to rewrite that stuff. That's going to be v1 squared plus v2 squared plus u1 squared plus u2 squared minus double that square root of u1 squared plus u2 squared times the square root of v1 squared plus v2 squared cosine of the angle theta. Okay. So here, on this side of my equal sign, I multiplied it out. Over here, I haven't changed anything. Notice now a bunch of things cancel. Hey, look. u1 squared is on both sides of my equal sign. So if I just subtract u1 squared from both sides, that's gone. Hey, look. u2 squared is on both sides of my equal sign. Right here. So I can cancel those out. Here, v1 squared and, my apologies, that should be a plus right there, shouldn't it? Why didn't anyone tell me? That should be a plus. Right? Negative times a negative is a positive. Same thing here. Negative times a negative is a positive. So here, this one and this one subtract away from both sides. And finally, this one and this one. You can subtract v2 squared from both sides, and those two go away. So now we're left with a much, much, much smaller expression. This has now become, well, let's see what's left. Negative 2 u1 v1 minus 2 u2 v2 equals to negative 2 square root of u1 squared plus u2 squared, square root of v1 squared plus v2 squared, times the cosine of the angle theta. Notice that I have a negative 2 that's common to both sides. Okay, so let me divide both sides by a negative 2. Here, just divide by negative 2. And this gives us, well, all the negative 2's go away. And this gives us u1 v1 minus, double negative makes that a plus, so plus u2 v2 is equal to the square root of u1 squared plus u2 squared times the square root of v1 squared plus v2 squared, cosine of the angle theta. But remember, theta is the thing we're looking for. Going back up to this problem, that's the angle that we're trying to find. We're trying to find the angle between those two vectors. So let's get that theta by itself. Let's move that stuff over. So here, let's get the cosine of theta by itself. We would divide on both sides by this. That would make this one go away, and it would put this in the denominator of this one. So this is u1 v1 plus u2 v2 over the square root of u1 squared plus u2 squared, square root of v1 squared plus v2 squared. Okay. Now we already know what these are. These are the magnitudes of u and v. Okay, so that's going to be the magnitude of u times the magnitude of v. And when these computations were initially done, when people were first discovering this stuff, they kept seeing this expression over and over again, u1 v1 plus u2 v2. So they decided if that's important enough to appear over and over again, it's important enough to have its own symbol and to have its own name. And hence, we defined the dot product. u1 v1 plus u2 v2. u1 v1 plus u2 v2. That's why the dot product's defined the way it is, because it keeps showing up whenever we were trying to find angles. So here, this is the dot product u dot v. And this will help you find an angle. All right? So we have a theorem, and I guess I did that backwards. Here, this is actually the proof of that theorem. So proof, usually I state the theorem first and then I prove it. I guess I ended up doing it backwards this time. Oh well. So here, this is the proof of a theorem. So let's just go ahead and state it. Theorem, let u and v be vectors, and let theta be the smallest angle between u and v. When we say the smallest angle, keep in mind that there is more than one angle between two vectors. If I have these two vectors here, u and v, here what I want is I want this little angle. I could go around the long way. I could try to find this angle out here. That's not what this gives us, though. This gives us the smaller of the two angles. So when we say theta, we mean the shortest possible angle. So let u and v be vectors, and let theta be the smallest angle between u and v. Then the cosine of that angle theta is going to equal to u dot v over the magnitude of u multiplied by the magnitude of v. So as a couple of examples, here the proof of this one was already given. We just finished doing that. So here the example, find the angle, find the smallest angle between the vector u, which is, let's just say 2 comma negative 3, and let's say the vector v is 1 comma 5. Okay. All right, we're going to go ahead and take first the dot product, u dot v. All right, well, that's simple enough. First component times the first component, plus second component times the second component, and that's going to give us 2, and that's a negative 15. So that's going to give us negative 13. Okay? Now we need to find the magnitudes of u and v, and we can do that by taking the square root of the sum of the squares of the components of u and v. So here, let me take the square of 2, then let me take the square of negative 3, add those together, and take a square root. All right, well, that's going to be the square root of, let's see, that's 4 plus 9, which is the square root of 13. And then let me find the magnitude of the vector v, which I'm going to do the same thing, but instead of using the components of u, I'll use the components of v. So that's going to be the square root of 1 squared plus 5 squared, which is equal to the square root of 1 plus 25, which is equal to the square root of 26. Just like that. And so now we get that the cosine of the angle theta is equal to negative 1, negative 13. Right, I'm going to take my dot product, that's going to go in my numerator, and then I'm going to take the products of the two magnitudes that I found. Just like that. Okay. And you say, well, you didn't want the cosine of the angle theta. I thought you just wanted the angle theta. Oh, okay, well then take the inverse cosine of both sides. Here, if I take the inverse cosine here, and if I take the inverse cosine here, that'll isolate my theta, and that'll give me that theta is equal to the inverse cosine of negative 13 over the square root of 13 square root of 26. And that's it. That's our answer. For application purposes, you might type that into a calculator, but if all you were looking for was the angle, that's it. You're done. But let's see. So what is that? If we want an approximation, if in a later section we'll be doing some applications, find the angle between the two ropes or something. In that case, here we would probably need to type this in somewhere. So let me take negative 13 divided by the square root of 13 times the square root of 26, and that's going to give us that negative number there. All right. And then if I take the inverse cosine of that, that gives me 135 degrees. So here that means that this is 135 degrees. And there we go. So the angle between these two vectors is 135. I chose these numbers completely arbitrarily. I didn't expect for it to get a nice answer. It usually doesn't. It'll usually be something like 116.115938.7 degrees. That was just a coincidence. So as the last example for the section, go ahead and try one. Find the angle, find the smallest angle. Theta between the vectors u, which let's go with 3, 4, and the vector v, let's go with negative 1, 2, because why not? All right, so go ahead and pause the video and go through and find an answer. Once you've found an answer, once you've found the angle theta, go ahead and unpause the video and we'll go through it together. All right, so let's take a look here. First, we want to find the dot product of these. So let's see, u dot v, that's going to be 3 times negative 1, that's negative 3, plus 4 times 2 is 8. And if you take negative 3 plus 8, that'll give you 5. That's your dot product. Okay? We want the magnitude of u, and that's going to be the square root of the sum of the squares of 3 and 4. That'll be the square root of 9 plus 16, which is the square root of 25, which is just the number 5. Okay? And we're going to need the magnitude of the vector v, and that's going to be the square root of the sum of the squares of negative 1 and positive 2, which is the square root of 1 plus 4, which is the square root of 5. And that one doesn't simplify. So we're going to get that the cosine of the angle theta is equal to, take your dot product, that's your numerator. Your denominator is the product of these two magnitudes. So 5 times root 5. And in fact here this simplifies, right? These divide out, and that's just going to give you that the cosine of the angle theta is equal to 1 over root 5. And so if I want to find the angle theta, I need to take the inverse cosine of both sides. Inverse cosine here leaves me just my theta, and inverse cosine here gives me my answer. So theta is equal to the inverse cosine of 1 over root 5. And that is my exact solution. Here I can give an approximation of that if I really, really want to. So if I take 1 divided by the square root of 5, that's going to give me that number. And now if I take the inverse cosine, that's going to give me approximately 63.43 degrees here. So that's approximately 63.435 degrees. So the smallest angle between those two vectors is 63 point something degrees, just like that. So that's the exact answer. In application, you might actually need an angle in degrees or something. So there we go. Note that if you have two angles, there is a small chance that the two angles will work out to be 90 degrees opposite of each other. That has a name. That's called orthogonality. That sounds like it's going to be more work, but it turns out that that case is easier to spot. So let's see here. Definition. Two vectors are orthogonal if their dot product is equal to 0. So the word we're defining is orthogonal. Geometrically, you can think of orthogonal as being meeting at a 90-degree angle. So here, geometrically, think of orthogonal as meeting at a 90-degree angle. Okay. That is not the best definition, mostly because orthogonal means things for things that are not straight-lined vectors later on down the line. In calculus and beyond, you'll talk about orthogonality in ways that geometrically would be very difficult, if not impossible, to think of. But for vectors, if you have just two vectors on a plane, that's a decent way to think about it. Right? This is not precise, but it is a way to help you remember what it is that we're talking about. But this is the precise definition. And you say, well, how is that any simpler? That looks like an extra layer of stuff. Well, sure, but if something's crossing at a 90-degree angle, think about what that looks like from the point of view of this formula. The cosine of 90 degrees. What's the cosine of 90 degrees? Well, that's going to be 0. Yeah, so? Well, that means that if I go back to this formula here, the cosine of theta is equal to this. But if theta is 90 degrees, then all this whole thing is equal to 0. Oh, but if this whole thing is equal to 0, that's a denominator. You can't make the denominator 0, so it must be the numerator that was equal to 0. Okay, so if this is 90 degrees, it's because the numerator was equal to 0. Oh, but since the numerator is the dot product, that means if I want this to be 90 degrees, I need this dot product to be 0. That's what that's telling us right there. As long as the dot product is 0, then you know for a fact that your two vectors are orthogonal. So for example, note that I have the vector u is equal to 5, negative 3. And let's say the vector v is given by, let's say 6 and 10. Then you would say, okay, well, the dot product of these two is equal to 5 times 6, which is 30, plus negative 3 times 10, which is negative 30. And that's going to give me 0. Here, I don't have to continue the computation at all. Because this is 0, that means if I come over here to the formula for finding the angle between the two vectors, well, that means that if that numerator is 0, the whole thing's 0. But the cosine of an angle is equal to 0, that means that angle is 90 degrees. So here, because this is 0, automatically you can conclude that U and V are orthogonal. And if the question was find the smallest angle, between U and V, here we would say, well, since they're orthogonal, the smallest angle between them is 90 degrees. If you didn't remember this and you proceeded and went through the whole formula, you would eventually find the answer of 90 degrees. But this is simpler. Once you get 0, you're done. Once you get 0, they're orthogonal. So the smallest angle between U and V is 90 degrees. And that's it. So this brings us to another definition. So let's start off with a couple of non-zero vectors. Let U and V be non-zero vectors. Okay. Now, let the vector U be composed of the sum of two other vectors. We're going to call those vectors W1 and W2. Here, these two vectors are not just arbitrary vectors. They are vectors which, the first one, we're going to say is parallel to the vector V, and the second one is perpendicular, is orthogonal to the vector V. Okay? Remember the definition of orthogonal, if the dot product of these two is 0. Okay? Before we proceed to finish defining this, let's go ahead and illustrate what we have. Let's say we have a vector U and a vector V, and these are just arbitrary non-zero vectors. Any vector is fine as long as it's not a zero vector. So I'll call this one U, and I'll go ahead and call this one V. And V doesn't have to be horizontal like this. It's just, for the sake of illustration, it's easier for me if I just draw it this way. All right, now, this vector U is going to be such that it's made up of the sum of two other vectors. But those aren't going to be just two random vectors. One of those vectors has to be parallel to V. So it has to run alongside V, just like this. Right here, so this one right here would be W1, and then W2 would be orthogonal, perpendicular to vector V. So like this. Right? So right here, U is made up of these two, where one of them is running alongside V, and the other one is coming straight out of V, perpendicular. Okay? In that case, W1 is what's called the projection of U onto V. And it's denoted W1 equals the projection, P-R-O-J, of U onto V. The subscript one is the one you're projecting onto. U is the one that's doing the projecting. Like this. So W1 is the projection of U onto V. Meanwhile, W2 also has a name. W2, which is really just U minus W1, this one is left over. This is called the vector component of U orthogonal to V. We don't use this one too often. The projection is the one that we're most interested in for most applications in this course. However, these two are defined at the same time, so we do put them together. Okay. Here, one way to visualize this, think of it as a shadow. Imagine V is the ground, and this is like a tree. All right, so here we have the ground, and we have a little palm tree. There we go. Palm trees have coconuts. There we go. There's coconuts. All right, so now it's a bright sunny day. Here's the sun. There we go. All right, so the sun, this object is not on the ground. However, it will project a shadow. That shadow is the projection. This is the projection of the tree onto the ground. The projection of U onto V. So the V is acting like the ground, and the U is acting like the tree whose shadow is being cast. The projection is that shadow. Not a perfect parallel to the, pardon the pun, it's not a perfect parallel to the image, but it does help give a little more of a solid feel to this. All right, so that is our definition. Okay, so how do we find one of these projections? So that brings us to a theorem. Let's say you have two vectors, non-zero of course, otherwise a lot of this stuff doesn't work. Let U and V be, actually I'm going to go ahead and write that, be non-zero vectors. Then the projection of U onto V, remember the notation, the way this works, U is the one you're projecting, V is the one you're projecting onto, U is your tree, V is your ground. The projection of U onto V is given by U dot V over the magnitude of V squared. Notice the dot product is a scalar. The magnitude is a scalar. Squaring a scalar still gives you a scalar. And a scalar divided by a scalar, that's a scalar. This is just a number. Number 5, number 12, whatever the number is. That's going to get multiplied by the vector V. So it's a scalar times a vector, just like that. This may seem a little intimidating, but the proof of this is almost entirely trigonometry. There's very little in terms of what we have here. And here you may even recognize U dot V over the magnitude of U times the magnitude of V. That would just be the cosine of the angle theta between the two vectors. Right? So that's not exactly the same, but it looks very similar to it. So I would imagine that's involved, yes? So let's talk about the proof of this. You might want to try this one. Or you might want to pause the video and give this a try if you, especially if you're planning to continue on to other math classes after this. Being familiar with proving things is a useful skill to have. Go ahead and pause and come back and confirm it together. All right, so the proof of this is really very geometric. Use a little trigonometry. Consider two vectors. And again, they don't have to be where one's horizontal, but I'm going to draw it that way because it's easier for me to draw. You say, well, what if one was not horizontal? What if it was like this? Well, then rotate it till it's horizontal. Right? Simple enough. Okay, so here's the vector U, and here's the vector V. All right, so what we're looking for is we're looking for this vector right here. This is the goal. Okay. Now remember, there is a second vector here that is perpendicular to the vector v, and when you add those two together, you get the vector u. All right, well, this is a 90-degree angle. These are parallel, these are perpendicular, which must mean this is 90 degrees. Okay, so if that's 90 degrees, well then we have trigonometry on our side. Let's call this the angle theta. Okay, well this is the vector u. Oh, I should draw it with a little arrow, right? And there goes a vector. All right, so this, if I take the side lengths, that's a triangle, right? So if I have this, that's a side length. Okay, well the magnitude of u would be that side length. And then I have this side length and I have this side length. And here's an angle. All right, well, let's see. This right here is my projection. Well, it's not. My projection is supposed to be a vector. This is just the length of a side. Oh, okay, well then that's the magnitude of my projection. Oh, well that's just cosine, right? Adjacent over hypotenuse. The cosine of the angle theta is equal to the adjacent side, which is the magnitude of my projection, over my hypotenuse, which is the magnitude of u. Like that. So right here, I could just go ahead and multiply this over to the other side, and I could get that the magnitude of the projection that I want, the magnitude of the projection of u onto v, is equal to the magnitude of u times the cosine of the angle theta. Oh yeah, but I know the cosine of the angle theta, that's given to me by a dot product, right? Here, that's equal to the magnitude of the vector u times the cosine of the angle theta is given by the dot product of u with v. Ooh, that's where that dot product's going to come from, isn't it? Divided by the magnitude of u times the magnitude of v. Oh, look, these are common. They divide away. After all, they're just numbers. So that means that the projection of u onto v has a magnitude that's given by u dot v over the magnitude of v. Oh yeah, but that's just the projection. Sorry, that's just the magnitude of the projection. I didn't want the magnitude, I want the full projection. Oh, well, I know how long it is. Now I just need to know what direction it's going in. Well, that's easy. It's going in the direction of v. Okay, so I need a vector that's in the direction of v, but that has this magnitude. Well, I don't know how to find a projection of, I don't know how to find a vector that's parallel to v that has that projection magnitude, but I do know how to find a unit vector in the direction of v. Note that I can take v divided by the magnitude of v. And that's going to be the unit vector in the direction of v. Over here, this is the magnitude of the projection So if I put these together, hey, here's my vector. Oh, but it's the wrong size. This is a unit vector. I need to scale it so that it's the right size. Oh, well, then I take this one, I scale it by this amount, because this tells me how long it's supposed to be. This has magnitude 1, so 1 times this, oh, it'll give me a magnitude that's this. So that means that my projection of u onto v must equal to, that's in the right direction, but it's only got magnitude 1. But by multiplying it by this magnitude, u dot v over the magnitude of v, that gives me this vector with the right size. Here, these two are the same, so I can say, well, the magnitude of v times the magnitude of v, I can write that as the magnitude of v squared. And then that's just a vector v, which is exactly what we were supposed to get. So here, to compute the projection of u onto v, you take the dot product of u with v, divide by the square of the magnitude of v, and then multiply the whole thing by the vector v. So now let's consider an example. Let's go ahead and find the projection of v onto w. Remember the notation. This is the one that you're projecting. This is the one you're projecting onto, where v is equal to the vector 3i minus 2j, which remember can also be written in component form as 3 comma negative 2, whichever one you're more comfortable with. They are interchangeable. And the vector w can be written as I minus j, or if you prefer, 1 comma minus 1. All right, so as we see, if you're projecting one vector onto another, it is equal to, we're going to take the dot product of those two vectors, that's v dot w, divided by the square of the magnitude of the vector you're projecting onto, so the square of the magnitude of w, and then that whole thing is a scalar. That dot product is a scalar, the magnitude's a scalar divided by a scalar is a scalar. That whole thing will be multiplied by the vector w, the one that you're projecting onto. Right? So now we can compute all of these and get our result. First, let's find v dot w, which is, we're going to take the first component with the first component, multiply it together, 3 times 1, plus the second component times the second component, negative 2 times negative 1. So that's 3 plus 2 make 5. So that'll be the numerator of our scalar. Our denominator, we're going to take the magnitude and we're going to square it. So here is the magnitude of w. The magnitude of w is equal to the square root of the sum of the squares of the components of w. So in this case, that would be 1 and negative 1. So you're going to square 1 and negative 1. You're going to add those and then take the square root. Now remember, you're going to square that. Well, when you square this side, this is the same as squaring this side, the square root squared just gives you the stuff inside. So when you ask for the square of the magnitude, really you're asking for just the stuff inside without the square root, since the square and the square root would simplify away. So really you're just asking for a 1 squared plus a negative 1 squared. That's 1 plus another 1, which is just 2. So that's the denominator of our scalar. And then w is the vector 1 comma negative 1, or I minus j, whichever you prefer. You may notice that I tend to prefer this form, but it really is interchangeable. It makes no difference. So that's 1 comma minus 1. And so when we multiply these out, after all, we simply distribute the scalar into our vector. That's going to give us 5 halves times 1. That's 5 halves, comma 5 halves times negative 1 would be negative 5 halves. And this would be our projection. Projecting v onto w would give us the vector 5 halves, comma negative 5 halves. You might wish to go ahead and give this a try. So for our next example, go ahead and give this a try. Find the projection of, let's use the same notation. Let's do v onto w, where the vector v is given as I plus 3j, or again, if you prefer, that's 1 comma 3. And w is given as negative 3i plus 6j. Or if you prefer, negative 3 comma 6. Those are interchangeable, yes? So go ahead and give this a try. Go ahead and pause the video, give yourself whatever time you need, and once you are done, go ahead and unpause and we can go through it together. Okay, as we see above, the projection of V onto W is equal to V dot W over the square of the magnitude of W times the vector W. Notice that this one appears only once, V dot, and everything else is W. V dot W over W's magnitude squared times the vector W. So this appears once, the thing you're projecting onto appears for all of the other ones. So now we simply need to compute these values and plug them in. We can find V dot W. After all, that's simply multiply the first two components. That's 1 times negative 3. Plus, multiply the second two components, 3 times 6. That'll give us negative 3 plus 18, which is 15. So that'll be our numerator. That'll be 15 over the magnitude of our vector squared. We see that that's really just the stuff inside the square roots, because the square root will go away. So the magnitude squared is simply the sum of the squares of the components without needing the square root anymore. Negative 3 squared plus 6 squared. That'll give us 9 plus 36, which is 45. So that is our denominator, 45. And then that's going to get multiplied times the vector W, which is negative 3, comma 6. Note that this can be reduced down, 15 over 45. You can divide top and bottom by 15. And this gives us 1/3 times negative 3, comma 6. And if you now multiply this W by 1/3, remember that's simply distributing the scalar. That's going to be 1/3 of negative 3, that's negative 1, and 1/3 of 6, that's 2. And so the projection of V onto W is negative 1, comma 2. Just like that. So that brings us to the end of our topic. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.